All right. Well, first of all, thanks a lot to Erlang Factory. I'm really excited to be here. Again, my name is Seth Falcon. I work at Opscode, and I want to share today kind of case study of kind of tell the story of why we ended up migrating our web API from a Ruby and CouchDB stack to an Erlang and MySQL stack. I want to talk a little. I'll tell you a little bit about how we did that and some of the lessons learned in terms of some of the tools. So I'll have some tips that we came across about using webmachine, which is what we used on the Erlang side. And I'll also talk some about how we approached the actual migration, which was pretty fun and in the end really successful in terms of not having people notice. But I need to give you a little bit of background just to kind of set the stage for the story. So Opscode, we make a product called Chef. And Chef allows you to describe your infrastructure, the configuration of your servers, and how they communicate with each other as code. There's a kind of a DSL on top of Ruby that you describe the configuration in. It's a client-server model. So you run, there's a centralized Chef server, and that's what's hosting the web API that I'm going to be talking about. And then you run the Chef client program on your servers, which we call nodes. So you'll hear me talking about nodes, and that's what I mean. I mean your servers that are running Chef client that talk to the server and make API calls. It's really great if you're curious about it. There are 4 of us here from Opscode, so come grab me afterwards or some other time. The Chef server API, so where we started from, written in MIRB, so a Ruby web framework since has been merged into Rails. We use Unicorn and Nginx to deploy that. So it's a stateless, horizontally scalable kind of setup. The Chef server talks to CouchDB for data. Talks to a authorization service, which actually we wrote in Erlang early on. It also talks to Solr for search requests. So a typical request is going to talk to the database and pull out some public key data to do authentication. It's going to pull, we're going to be focusing on the node data. So node data from CouchDB. Based on some analysis of our data set at the time that this story is unfolding, our median node size was 22K, third quartile was 44K. So the data involved, not tiny perhaps, but certainly not large by any means. After pulling the data, it's going to do an authorization check. And then depending on the verb, if it's a get, it's going to return that data. If it's a put, it's going to process the request body, update the database, and then send back a response. That served us really well for a while, but as the product got more popular and our user base grew and the load increased, things started to not go so well operationally. What you're looking at here is average API response time across all of our endpoints. I know the numbers are way too small to see, but the wiggly peaks there are around 500 milliseconds. So we really didn't like that number in terms of we really thought we should be a lot faster. And also it really was concerning just how wiggly things were. We'd really like to see something more reliable. So things weren't going so well. The other thing that was starting to happen operationally is that we were having sort of mini outages on kind of a regular basis where things with CouchDB weren't going so well. What you see here is the uptime graph of our CouchDB server. The peaks represent times that we had to restart CouchDB because of places where it got stuck, and that was sort of the resolution. The gaps are places where we failed over to we have an active passive high availability, so those to sort of ignore the gaps. And then way on the right there, where things get more regular, is where we finally just had a cron script that restarts it on a regular basis. The other thing that was starting to happen is that the stack overall was consuming a lot of resources in terms of RAM and CPU on the database side, but mostly RAM on the server API. So that kind of sets the stage for, OK, we need to do something. And so in stepping back, one of the things that we wanted to ask is, well, OK, like how bad are things? Like what, do we have something can we expect that if we change, it's going to get better? So we asked how much RAM should it use? And this is a totally made up number, but kind of good for some context. So I figured, well, third quartile node size was 44K. So that's sort of worst case-ish. And at the time, our load was about 60 requests a second. So some kind of made up, unrealistic lower bound for how much memory we might need to serve our requests would be 2.7 megabytes. Obviously not a realistic way to do a computation. You've got code that's going to be in memory. Of course, in any kind of framework, you're going to have some copies of the data, and so on. So I don't know, multiply by 10 just to get a next increment of a total wild guess, right? But we don't have to guess. We can actually measure. So we went and looked at our unicorn workers and found that actually at rest, shortly after startup, we were seeing RAM use of 100 megabytes. And with the unicorn model, and this is also where we're sort of starting to step back and think about the model of hosting web services with a stack like Ruby, where you have a unicorn process, separate process for each request. So your concurrency is one request per worker. Under load, what we were seeing was actually a larger number. So we were seeing 204 megabytes per unicorn worker under load. And so you get to a point where your concurrency starts to be actually limited by how much RAM you can throw at the problem, which is kind of a funny thing. So how does that work out? We were running 12 workers per server. We had 8 servers. It kind of adds up to this shocking number. So we're pulling JSON out of a database and turning around and serving it back. And to do this with what is essentially a modest load was 19.2 gigabytes of RAM. OK, so that was motivating. It really felt like there was a fundamental thing with the way the model of using Ruby and Unicorn with the separate processes where there's just a fundamental limitation. Also some details of the Ruby garbage collector that are unfortunate with the way that the Ruby garbage collector sweeps through the whole object space means that if you do forking with copy on write, you don't actually get that benefit, because as soon as anything touches that, as soon as a garbage collection runs, all of the memory is touched and copied. Unicorns eat RAM. OK, cool. So looking for other solutions, and we had already used Erlang some in-house, and actually for a little web service. So we had some experience with Erlang and webmachine, and we really felt like the per process garbage collection was going to be a very clear win for Erlang with this kind of model. One of the things that we saw with the Ruby, again, sort of some issues with the garbage collection, is that as soon as you get one large request going through a unicorn worker, the RAM use for that worker tends to just stay allocated and high. It doesn't give it back. And so conversely, we were confident that even if we had that same sort of spike on the Erlang side, that process is short-lived. It goes away, memory is returned, and that's kind of nice. So webmachine is this fantastic tool, open source, put out by the folks at Basho. Really great toolkit for quickly putting together REST services, and so that's what we did and started and ported our node and search endpoints were the first ones to go to webmachine. So I kind of want to take a little pause in the story and share some of the what we learned from implementing and working with webmachine a lot, because I think it's a common enough framework that there might be some value in sharing some tips. So I've got I've got 4 tips, and I'm going to tell you a little detail about 2 of them, and the last 2 are in the slides with some detail, or you can ask me afterwards, but I don't have time to go into it. So just to run down them quickly, first tip is about not forcing your application logic into the kind of callback structure of webmachine too tightly. The second tip is about one approach that we came up with for sharing the resource functions across resource modules. We also found it useful to use the finish request callback for logging and metrics and to sanitize error responses so we don't return stack traces. And we also came up with a method for manipulating the dispatch list to inject configuration across all of the resources in a nice way. And so that's kind of fun. So with webmachine, the model is that it models the HTTP or HTT protocol as a big state machine. This is a diagram that kind of shows the flow and sort of maps to the callback functions. I know you can't read it, but you get a sense of kind of its complexity. And it helps you get REST resources to get that right. But what happens is that your application logic doesn't always fit into these callbacks. So a couple of examples. One of the things that happens early in processing a request is there's a callback called malformed request, where if it's malformed, webmachine will return a 400 for you and otherwise go on to the next steps. So if you've got a put or a post kind of request that you're handling, in order to answer that question, you have to parse the response body to determine whether it's malformed or not. But the functions the callbacks that actually like handle that post and put it in the database come way later. So the way you typically get around that and kind of work with that is that you memoize the result of that in the resource state. And so that's one approach of kind of fitting your application logic into the web machine and into the shape of the HTTP state machine. Another example is for the forbidden request. And so what happens is, you come in and you do forbidden, and then I've kind of cut the diagram, and all this other stuff happens. And then way down later in the state machine is the part where you call resource exists and decide whether it's a 404 or not. Now, in most web applications, in order to decide if someone is authorized, you have to fetch something from the database to look up an ACL to decide if they're authorized. So like, you're going to know if it's not found pretty early on. And I think a lot of people, and myself included, when I first started with webmachine, I tried really hard to make sure all of the kind of logical steps of the callbacks in webmachine that I was, that in the resource exists callback, I was doing that task in my application. And that's just you can do that as much as it fits, but when it doesn't fit, I think it really helps to kind of give up on that notion a little bit and relax and not stress out about it, because you'll hate your life less. So for that case, what we do is, here's an example of a forbidden resource, and if we get sort of a not found case, we just go ahead and exit early, halt. We sort of get rid of the action at a distance, and perhaps that's not the true web machine way, but it really was liberating to not try and map too closely to this. Okay, and then our innovation, such as it is, on sharing resource functions really boils down to one realization. So all resource functions use a state record, and what we came up with was, if we defined a common state record, that allowed us to write shareable resource functions. So what we did is define something that we called the base state. And it has fields that are shared across all of our modules. So here I'm showing you request ID, but for us we also have like an organization ID and some other details that make sense across modules. And then we also have a resource state field, and the idea there is that for each resource module where there is specific data, we define a record type that's used only in that module, and that's kind of a nice separation, so that the common bits have a common record state to work with, but there's still a place to hang and memoize the resource-specific stuff. So for the node endpoint, we would have a node state record that would go in the resource state field. And so using that allowed us to share resource functions. So we have a module that we call chef rest WM, and so here's an example where we're defining service available is authorized in finish request. We have this little helper macro that helps define it, still export it, and then that macro is really simple. You give it a module and a function, and it just kind of, it's just a little typing saver essentially to put the definition. So kind of, when we were developing this, we actually looked at, well, maybe we should do a parse transform to do the sharing. And we kind of came up with this and really liked it because it's dead simple. There's really no magic. But we still get to have some common modules where we share a lot of the logic across the different resources. OK, so skipping the finish request details, skipping dispatch args for common config. OK, so some of the good stuff. So how did we do? So we ported the two heaviest endpoints, the search endpoint and the nodes endpoint. We ported that from the Ruby and CouchDB to Erlang with webmachine and MySQL. So memory-wise, considerably better. So we were idle, 19 megabytes, loaded, 75 megabytes compared to 204 on the Ruby side. Now, that number is a little deceptive because that may seem kind of close, but when you map that to the way that you have to have the numerous unicorn workers, so we were using across our cluster 600 megabytes compared to 19.2 gigabytes for the Ruby. So we were pretty pleased about that, that savings. So the other part of the story, which I haven't given as much detail on yet, is the CPU use. And so we did do some profiling before we got started, wondering where the Ruby code was spending its time. So we thought, is it the database calls or JSON parsing? Is it the public key crypto that we're doing to authenticate request? Maybe it's garbage collection. Maybe it's garbage collection. So it turns out with the Ruby code that over 40% of the time was spent in spent in garbage collection. What you see here is on one of our API servers, the break there in the middle of the graph, the drop in CPU use was when we deployed the Erlang code onto the same box. So we're serving all of the same endpoints, but the break occurred when we moved two of those endpoints to Erlang. So not only did we save on RAM, but we also got a nice CPU benefit. And again, we're doing the same work, just in a different stack. So that was good. So that's sort of the first half of the story of some of the why, and a bit of the how on moving from the Ruby stack to the Erlang stack. So now I have the harder part of the story to tell, perhaps. There's this thing that happens, right, with a new technology. You find a new technology, you're really excited about it. It's kind of like a new relationship, It's solving all of your problems. Everything is good. There's kind of a honeymoon period. Then over time, perhaps you start to encounter some limitations, some problems. And maybe you find out how you're using the technology wrong. And maybe sometimes you can work it out and you try, And then other times it becomes something where you can't work it out and you have to break up. And so that's what happened with us and CouchDB. We had to break up. Now, that isn't to say CouchDB isn't a perfectly good solution for other applications, but for our application, we realized we had to part ways. I want to tell you a little bit about why. So our load involved a lot of frequent gets and puts of this Node.json, so this 22K Node.json. And the result of that with CouchDB's append-only B tree is the rapid accumulation of garbage. That means that you have to spend a lot of time compacting, and the compaction in CouchDB is something that you have to do from the outside manually. the compaction impacts your latency because you're doing stuff with the database and it's got to do some locking. And it actually turns out that, I believe up until recently, but certainly with the versions that we were using, that CouchDB actually has serialization, locking essentially, around accessing a single database. So we were seeing higher latencies and not getting as much concurrency as we thought we could have. And that led us to a design in which we had more databases because we didn't want to have fewer databases because that meant less concurrency. But then we ran into problems trying to make use of the replication feature in CouchDB. So we have lots and lots of databases. We each and we tried pretty hard to get the replication to work, and we couldn't make it work reliably. It's not to say that it doesn't work at all, but we weren't able to get it to work for our case. And so that meant that we had certainly a lot of the advantages of Couch's REST API and the document-oriented database and a lot of those nice features. But we weren't able to take advantage of the replication and do HA in the sort of Couch way. So we had to move our HA to use DRBD active-passive HA, which works really well, but doesn't give you the magic scaling ponies of having multiple databases, which can be nice. Another thing we ran into was file handle leaks, where over time what we saw is the CouchDB process taking more and more memory, the box actually going into swap, although not actively swapping, which was kind of interesting, but also indicative of a resource leak type thing. So file handles would get allocated and never returned. And this was in many cases the main reason why we needed to restart CouchDB, and that would resolve it. So needless to say, it became an operations thing. It became the component in the system where when we were having problems with the site, when things got slower or we were seeing errors, that's where we kind of started to look first, and a lot of times that was the right place to look first, and restarting it got things going. So all of these reasons motivated us to look elsewhere. So in stepping back, what is it that we need from a database? So clearly we need something that's going to be happy with a pretty write-heavy load. We're pretty much always doing gets and puts, and that's the heaviest part of our load. Sophisticated queries is maybe a bit strong, but we definitely have a problem that is not a simple key value problem. There's a lot of parts of our problem that can be solved by a simple key value lookup, but an essential part of the sort of chef system and the APIs involves collections of things. So there's a call to get the collection of all nodes or the collection of all roles. And so secondary indices and an easy way to do that is a fundamental thing that we needed. And then we need to be able to have it be highly available, and that's kind of a minimum bar. I imagine there are those of you wondering to what extent we explored other NoSQL solutions, and we definitely did do some investigation there. But we also asked ourselves kind of the converse question of why not SQL? And as we were kind of looking at our data and looking at our load, what we realized is that we really didn't have a large data problem. Our data set size is actually pretty modest. And given that we have this need we have a write-heavy load, we have a need to do queries that SQL can do very easily, we decided to look a little bit more closely at implementing the old school way. So we did some measurement, actually used another tool from the folks at Basho. They have this Basho bench utility that allows you to kind of define custom drivers to do benchmark analysis, and then it creates data, and then it has an R script that uses R. If you're not using R, it's a really great tool for interactive statistical data analysis. And it makes really pretty pictures like this, And so we were able to test our theory of taking the node, the JSON blobs that represent the node data and storing them as blobs in MySQL. And indeed, we saw orders of magnitude more throughput. And so that worked really well. So we went ahead and moved forward with replacing the data store with MySQL. Just in terms of why MySQL as opposed to other things, we definitely looked at Postgres, and in fact, our private chef product that you can install in your data centers, we deploy that with Postgres, so we have an abstraction layer that allows us to talk to different databases. But the main motivation for us at the time was that we already were running MySQL in production for some other service, and we had on the team fairly deep expertise in terms of operating experience with the replication and backup of MySQL. And so, kind of all things being equal, those factors were really worth considering. Yeah, so we replaced CouchDB with MySQL while the system was running. Yeah, so like, like we talked at the time, we were like, yeah, this is kind of hard. It's like, changing the tires on an airplane or in flight or something. And so then I was Googling around for funny images or something. And this is not the only one on the internet. Just like, it's like this thing. Like there are, yeah, this is like a thing you do. You go in the desert and you turn your car sideways and change the tires. Like really, there's lots of like people, I don't know. Wow. Okay, so live migration starts out pretty easy, kind of three simple steps. So for us, each of our customers has an organization on the site. So the site is multi-tenant. We term each organization an org, so I'll probably use that terminology. So you put the orgs into read-only mode. So that means the Ruby API basically gets set up so that whenever it receives a request, it just, for a write, it sends a 503. Then you can copy the data from CouchDB to MySQL, and then you can change your routing and send requests over to Chef. So that's our code name for the Erlang stack of the API. Okay, so there are some details. Gets a little bit harder. So you need a tool that's going to coordinate the feature flipping. So that's the thing that's going to take an org and put it into read-only mode. And you need some coordination around updating the config of the load balancer and making sure it recognizes the updated config. You don't want to do this org at a time because you have lots of orgs, and you don't want the overall migration to take longer than needed, so you want to do batches. And then if you're doing batches, you want to sort of keep track of where the batches are and keep track of individual organizations. If a support request comes in for some reason, you want to be able to quickly determine whether an org is migrated or not, or in the process of migration. You know that nothing goes according to plan, and that you'd really like your migration script to be able to recover from a crash of some kind, because that's going to happen, and you don't want to have to start your migration from scratch, things like that. And then, as we talked through our plan and we kind of thought we understood the problem, we realized there's even some further subtleties and details that make the problem a bit harder. So the main challenge that we didn't realize until sort of talking through the details a bit more is that it's all fine and well to set a feature flipper and put an org into read-only mode. Incidentally, we can do that just for the node request, so that when an org is read-only, customers can still do other things with their org. It's just they can't write to nodes when they're in that state. So imagine a write request comes in, gets sent to the database. The database, for whatever reason, is taking a long time to process that and get back. Meanwhile, you have your feature flipper turn the front end to read-only mode. Okay. And so once it's in read-only mode, you'd like to think that you have a consistent state to copy the database, except you have a write that is pending. And so you should wait until that write is done. But then you need to know when it's done. So what we ended up doing, we added Redis to our migration tool stack, instrumented the Ruby code to track in-flight requests. So each time a write request comes into the Ruby stack, it updates a set in Redis and says, hey, I'm working on a write request. When it's on its way out, it removes itself. And so this way, Mover, which was the name of our migration utility, could poke the feature flipper pokes the API and says, go into read-only mode. Then Mover can poll Redis and say, hey, is this org actually in read-only mode? Yes, OK, now it can migrate the data. It can hup the load balancer. Of course, we had to add some extra complication in terms of error handling so that if an org had problems, some kind of data consistency or otherwise, we wouldn't want to leave them in a read-only state, so we'd want to log it, track that state, and then flip them back. And so after we had worked through this, we had to actually implement this migration utility. And the first thought was actually that we were going to script this up in Ruby. Our shop overall does Ruby and Erlang, and this feels in a lot of ways like a scripting task. You can kind of imagine how you go through the different steps and how you'd have helper functions that kind of set that up. But as we were looking at it, there were kind of two things that led us to go in a different direction. One of them was sort of a pragmatic thing, which is that we had just written all this Erlang code to take data and put it into MySQL, and so it would be nice to just reuse that and all of that for the API for the purposes of the migration. And then the other thing was observing how what happens to an org is really a little state machine. It starts out in an unmigrated state, then it goes into a read-only state but may have in-flight requests, then it goes into a read-only and no in-flight requests, and migration can proceed, and then it's in the migrating state, and then either it's completed or it's errored out. And so that kind of led us to the somewhat surprising, like if you'd said ahead of time, in the past to me, hey, you're going to implement the migration tool as a genfsm in Erlang, I would have said, like, did you just tell me to write a MapReduce function? But actually, it worked out really well, and it was actually one of the first times that I had really heavily used genfsm. But and this is kind of an unusual maybe use case for it, but I really like how it turned out, and I would do it again. And so we kind of scripted with genfsm, where all of the kind of helper functions that you would imagine in this sort of a script map to state functions. And then the server state that you pass through gives you a really nice organization to keep that state nice and orthogonal from your functions, and that made it a lot easier, along with, of course, the supervision tree and that sort of stuff, to make the migration tool fault tolerant so that it could crash at any point and it could recover and know where it was. Kind of in the diagram, you can see we've got debts over at the bottom, and so we serialized all of the state at various points to a local debts file so that everything was locally coherent and could be restarted. And kind of even better, you get a free REPL for your tool, which is a really powerful kind of setup. So you can start it, and then you can ask it questions about status, and that's you kind of get that for free, and that's just a really nice model to have, especially for an operational tool like we were building. So overall, thumbs up on OTP, genfsm, happy tools. I feel like that really helped us in terms of just keeping the tool organized, but also in terms of its robustness. And then also just kind of Erlang in general with kind of the process isolation. So we actually had two genfsms. We had a manager genfsm, and then we implemented the workers. So each org got its own worker to affect the migration, and that worker was a behavior that was a GenFSM so that we could kind of factor out the common bits for the different data types for future migrations. And if anything went wrong with a particular org, the manager was able to deal with that and know about it. So there were just a lot of things that whole OTP setup really helped with. Yeah, so how did that go? Anyone who's done big things in live production systems knows that things very rarely go to plan. We had done a lot of testing. We had done time measurements and estimates. We thought the migration would take about 3 hours. We were working on it for 3 days. Kevin here can attest to that. We worked together on that. So that was the bad news. That was pretty terrible. There was a lot of fixes that we had to come up with and unexpected things that happened. The good news was that I really didn't lie. We were able to accomplish the migration without interrupting customers. Individual customers were in this read-only mode for under 5 minutes, in most cases under a minute. I think we had maybe one person give a support ticket about the issue, and then it turned out actually that their issue wasn't, in fact, the migration. So that was really exciting. Cool, I better speed up just a little bit. I want to show you some results of what happened when we moved the data off of CouchDB and onto MySQL. So this first one is CPU usage, CouchDB, MySQL. The sort of peak that we were running at was at let's say a little under 600%, so that kind of maps to using 6 cores. After the migration, we dropped down to about 400, so about 4 cores. I don't know if you can see that little bump, but that's what the MySQL database had to say about it. Here's that same graph, but looked at as load average. So there, we were, say, at a load average of 7 and dropped to 2.5 or so. On the MySQL side, totally different scale. Instead of going from 0 to 10, it goes from 0 to 1, and we went from 0.2 to 0.3. So that was kind of appealing. But CPU use isn't what really matters. What really matters is the overall latency of the system. So here's our average API latency. So you've got the wiggle, 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 and around, a little under 500 milliseconds, and then boom, real nice. Drops were a lot faster and a lot more reliable, and that's across the board. In fact, this graph is the roles endpoint, which did not migrate, so it's still in Ruby and it's still in CouchDB, but by taking the load off of CouchDB with our heaviest endpoint, this is the 90th percentile latency, wiggle, 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 and yeah. So this was cause for some celebration. We had a little dance party.
Check it out. Wiggle, 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 yeah. Wiggle, 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 yeah. Wiggle, 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 yeah. Wiggle, 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 yeah. Do the wiggle, man. I do the wiggle.
Here's memory use on the database. We didn't get a big benefit in Couch because we're still using Couch, and so you don't see a drop there. The red on the top is swap, but MySQL looks pretty nice. This graph may be kind of hard to read from the distance, but this is CouchDB write metrics. And so before the migration, we were running about 10 writes per second, and then afterwards it drops to sort of 0 per second. This one, it was kind of a tear-inducing graph for us. Looking at Ethernet traffic, we're sort of just under 100 megabits, and then drop way down. So that's kind of testament to the node data that we were serving out of Couch was kind of somehow a large enough volume to have a real effect. One of the things that we did in putting the data into MySQL is we compressed it with gzip. And so when you look at network traffic after the migration on the Chef server, you see this really nice drop in inbound traffic because the data we're pulling from the database is now compressed. So that was a huge win. And that was something that we weren't sure about, but I showed you the Basho bench measurements, and that was a case that we measured. Does gzip actually give us a throughput advantage? And absolutely It did. So thanks for your time. That's kind of my story of the migration, of why we did what we did, a little bit of how we did it. So yeah.
Any questions?
There we go. So why'd you pick Couch in the first place if you're doing lots of really write-heavy stuff?
So that's a good question. I mean, it sort of goes back to the history of Chef and how it was developed. So I wasn't around. I wasn't around for that decision, so it's a little bit hard for me to give an answer. Yeah, I mean, it had a lot of nice things in terms of helping to get the product jump-started really quickly. I think the development went really quickly. I think it was really hard to see where the scaling issues and what the load was going to look like at the time that technology was chosen. I mean, so that's also part of it.
Would you reconsider using Couch now that it's evolved and developed a little bit more and seems like it solved some of the problems you guys had with it? Actually, to add to that, Big Couch. And the reason I'm saying that is we had exactly the same problems we went to Big Couch in. I haven't thought about it before.
I guess the most diplomatic thing I could say is it's sort of a timing thing. So I think we actually, I believe we did some experiments with Cloudin, which is Big Couch, yeah, or is that right?
There was
Yep.
some experiments, maybe a little premature.
Right. I mean, it was early. It was early days, and I mean, it's a timing thing. And I should also mention that in terms of some of the things you're seeing. CouchDB is a young product, so yeah. I mean, it's going to evolve and get better. I think for now, for our use, I think we found a solution that feels like it solves a lot of problems in a nice way for us. So I don't really imagine us going through the effort of migrating back.
Which MySQL and EPG SQL drivers are you using, and have you had any problems with them?
So let's see if I can remember the names off the top of my head. We are using MySQL. The branch from Eon Blast.
Okay. Yeah.
Is that right? I'd be happy. Come find me. I'd be happy to share that. And then we're using the EPG SQL driver. We did find some problems with the main branch there, although we put some patches that we run internally, and since then have found Anton, who's sitting there, has a fork of the EPG SQL library that has some really nice fixes, and actually our plan is to start using that because it addresses those. We started off using Poolboy. We ran into some problems with Poolboy that I believe have since been fixed thanks to John Hughes. And quick, what's that? Okay. So right about the same time that they were doing that debugging work, we were encountering the same issues with that tool in production. I had written a pooling library a while back, and I sort of cleaned that up, and we're now using Pooler, which is available on GitHub for our connection pooling, and that's been working really well. So.
You might have addressed it. I came in a little bit late, but how much of this rewrite ends up in the open source Chef server, and how much of it is going to be, what's Couch's future there? Is it going to be end of life completely, or?
My understanding is that we will be open sourcing this Erlang port, and that will include the relational database driver bits.
Yeah, if anyone's got questions about that,